back. So let's continue our discussion over the discrete random variable. So this will be the last part of having the discussion over the discrete random variables. So what I would like to, and today we'll also begin our discussions on the continuous time random variables. But I'm sure that it's not going to take much time because that's really analog to what we have done in case of the discrete random variable, actually, at least the theory. Okay, so the last topic that I would like to do is basically that, okay, if you have more than one random variables associated to an experiment, okay, so experiment, so in an experiment we can have kind of a more than one random variable. So I'll just write one example of it, and we'll do more examples of it as well. Then what we can ask is that, okay, if we do some kind of algebra of those random variables, then what would be their expectations and variances actually. So the last bit that I would like to talk about is about that expectation of, say, sum of random variables actually. So this would be a very useful trick, basically, that we're going to later on use to do several practical things actually. Okay. Let's start with an example. Imagine you flip a coin 5 times. 5 times. Okay. So we know what would be its sample space. And say X represents the number of heads in first 3 flips up. Okay. First 3 flips, and Y represents the number of heads in last 2 flips actually. 2 flips. Okay. And if I say Z is the total number of, represents the total number of heads in all 5 flips, then obviously Z can be treated as X plus Y. In other words, the total number of flips on all in all 5 flips is basically the number of heads on first 3 flips and plus the number of heads on last 2 flips actually. What values X is going to take? X is going to take what? X is going to take, so in first 3 flip maybe no head comes, okay, maybe 1 head comes or 2 head comes actually. So it is going to take basically maybe all 3 heads can come actually. Okay, so it takes values 1, 2, 0, 1, 2, 3. Okay. What values Y is going to take? So on the last 2 flips, okay, the final 2 flips, no head can come, 1 head can come, or 2 heads can come actually. So what values Z can take actually? We know Z can take values, if the Z is representing the total number of heads in all 5 flips, so it can take say 0, 1, 2, 3, 4 and 5. Okay. But you can also get these values by doing what? by adding the values of x to adding the values of y actually. So it's going to be 0, plus 1, plus 2, 1, 2 and 3 and 2 plus 0. So you don't have to repeat the numbers actually. Okay, so you still get, so it makes sense actually that z is going to take these values. But I want to take this notion more rigorous. Okay, so consider a particular outcome. Consider, say, an outcome, say omega, okay, of the all 5 point flips actually, and say omega is this actually. So it's head, tail, okay, head, tail, and head. Okay. By the way, what was the definition of the random variable? The definition of any random variable that it's a function actually. It's a special kind of a function, but for now we are assuming it, a good function. Okay, it's a function from the sample space into the values with R actually. Okay, so any random variable is a map from sample space into the R. Now this guy is an element of sample space. The question is, what would be x of omega? Okay, so calculating x of omega is like saying that, okay, in first 3 flips, how many heads are coming? So in first 3 flip, how many heads are there? So it's going to take value 2. What would be the y of the omega? So y does not cares about what happens on first 3 flips, but it cares about what happens on last 2 flips actually. So the y is going to take what values? So y is the number of heads on the first on the last flip. So you're going to have what you call value 1 actually, last 2 flips. So if z is representing, okay, the number of all flips, so one thing that you can clearly see from here is that there are 3 heads actually. But you can recover the 3 heads by summing up the number of heads over the first 3 flips and the number of heads over the last 3 flips actually. Okay, so this is what really the rigorous meaning of what you call summing the 2 random variables is. So when I say that z is the sum of the random variables x and y, then what does it simply means that z operated onto an outcome is going to be equal to first random variable operated onto that outcome plus second random variable operated onto that outcome actually. Okay. So this is really what you call roughly is the rigorous meaning of adding to random variables actually. Okay. And this must be true not only for this omega, but for any omega in the sample space omega. Okay? Alright. Let's try to see the consequence of this definition. Okay, so we can immediately prove an interesting theorem and a proposition actually, that you can rewrite the definition of expectation, not only terms, so we know that the definition of expectation of a discrete random variables can be written in the terms of the values that it takes times the probabilities of those values actually. But you can also write the definition of the expectation in the terms of the elements of the sample space actually. So in the terms of the elements of the sample space. So here's an interesting proposition, and we will later use this proposition to compute to prove a theorem that is going to give us that how to compute the expectation of sums of the random variable actually. Okay? So here's a proposition. So what does the proposition say? The proposition says that if you want to compute the expectation of x, where x is a discrete random variable, it takes whatever values, then you can compute this expectation by doing what? By taking the sum, okay? So previously, recall the definition, so of the expectation in case of the discrete random variable that we have done. So x takes these values x1, x2, x3 and so on and so forth, okay? But we have to also keep that when I'm saying that x is equal to x1, I mean, when I'm writing x equal to x1, interestingly, basically, this is not just an equation, but it's a set actually. So what does this actually mean is that, you know, this is the collection of those omegas from the sample space whose value at x is equal to x1. Is equal to x1. So from this example, if the z can take value 3, okay, in the previous example, if z can take value 3, it's not the only one omega for which you have z equal to 3. There can be multiple omegas actually for which z is 3. So for example, one is this, but if I take, you know, say h, t and t and h, this is also going to, so z of this omega is also going to be 3. Okay? But the x of omega is going to be 2 and y of omega is also going to be 1 actually. Okay? So when I am saying x is x1, what mathematically I am saying is that, okay, I am talking about a set of the outcomes of the omegas for which, set of all those omegas for which x of omega is equal to x1 actually. So for example, before getting into it, maybe I should clear up this thing so that it can make sense. So for example, if you want to have say z equal to 1, okay? So in how many situations you can have z equal to 1? So z equal to 1 is a set actually, in which there are all those outcomes in which there is only one head. And how many are going to be there are outcomes in which there is only one head? So you can have head, tell, tell. So this is one outcome. And tell, head, tell. This is another outcome. So there are going to be 5 such outcomes actually. I hope you understand it. Okay, so there will be exactly 5 such outcomes. So T, and H actually. So there will be at least 5 such outcomes. But what would be the Z of each of these outcomes? So Z of each of these outcomes is going to be equal to 1. Okay. So I talked about it previously basically, but I would like to emphasize on this that when the Z is taking a value, particular value, there is a set behind it actually. So you're saying that, okay, what are those omegas for which, you know, the Z takes the values 1 actually. So these are all those omegas. These are all those sample points for which the Z is 1. Are you getting the point? Okay. So what we can do, what I would like to do is that I would like to write the definition of expectation of x in the terms of sample space, in the terms of sample points actually. So expectation is the sum over the omegas, you know, what omegas, all omegas that you have in sample space omega, and this is equal to what? The x, so for each such omega, take the x of omega and multiply it with the probability of omega. So let's call P of omega as the probability of omega. Okay, so what is the probability of each of these omega? So for example, what is the probability of this half? Okay, so it's going to be say 1/2 power 5. Okay, so probability of this outcome is 1/2 power 5. And each one of this is 1/2 power 5. Okay, so that's another way to write what do you call the expectation of x. So इसमें लिखेंगे कैसे? So take all those, so take all omegas from the omega, substitute them into the x and multiply them with the corresponding probability. That gives you the expectation of x actually. So I want to show that our classical old definition of expectation of x can also be written in this manner actually. So here's a quick proof of it. Okay. So here's a quick proof of it. So suppose that x takes values x1, x2, x3 and so on and so forth. Okay, and for each value x equal to xi, in other words, as I said, what is x equal to xi? So x equal to xi is, let's give this set a name, say Si or omega I, whatever. Let's call this omega I, is the collection of the omegas, okay, from the omega for which x of omega is equal to xi. So you collect all those omegas for which x gives you the value xi. So it's going to be this set, or I'm giving it a name omega I actually. Okay, so with this notation, let's get back to the definition of expectation of x. So what was my definition of expectation of x? So our usual definition of expectation of x is that, okay, you take the sum, say I equal to 1 to infinity, of xi multiplied by the probability of x equal to xi. This is what the probability is, or the what do you call expectation is, the classical definition. पहले जो definition पढ़ी वो यही. Now what is this set? Okay, this is not like a probability of an equation actually. So the probability measure is a map from sigma algebra to the what do you call interval 0, 1. So the probability measure always acts on a set. So even if you write an equation in P, ये equation नहीं है, but this is a set actually, this set. Okay. So I can write this as I equal to 1 to infinity xi and the probability of what do you call omega I. Okay. So I can write this as probability of omega I. Now omega I is what? जैसे we talked about z equal to 1. तो z equal to 1 में 5 outcomes थे. तो इन omega i's में भी हो सकता है एक outcome हो सकता है एक से ज़्यादा outcome हो, या हो सकता है कोई भी outcome ना हो. So there can be multiple outcomes in these sets actually. तो अगर मुझे से probability of z equal to 1 चाहिए, so what I need to do? I need to calculate the probability of this outcome plus probability of this outcome plus probability of this outcome and the probability of this outcome. and sum up all these probabilities actually. So that will be the probability of z equal to 1. So similarly, अगर आपको probability of omega I चाहिए, so I can write this as I equal to 1 to infinity xi, so I can say that this is, ठीक है, the sum of those omegas which are in omega i's, ठीक है. So this is like taking the sum over those omegas which are in omega i's and summing over their probabilities. So P of omega. So P of omega क्या है? So यानी अगर आपको probability of omega I चाहिए तो आप कहेंगे omega I के अंदर जो outcomes हैं उन outcomes की probabilities का sum कर दें तो आपको probability of capital omega I मिल जाएगा. So I can write this in the terms of the sum actually. ठीक है? This is what it is going to be. Now I can do what? I can take this xi and multiply inside. So मैं इस xi को इस sum की हर term के साथ multiply कर सकता हूँ. So this would be like saying that I have a sum I equal to 1 to infinity and sum omega in omega i's, ठीक है? And I have xi times the probability of omegas. This is what it is going to be. ठीक है? Now अब मुझे ये बताइए इस सेट में यानी इस ओमेगा I में what value x is taking, so the x is equal to xi. So I can rewrite this expression in the manner, so this is like I equal to 1 to infinity and I can write sum of omega in the set omega I, और xi को मैं लिख सकता हूँ कि this is same as x of omega times the probability of omega. क्यों मैं ऐसा लिख सकता हूँ? Think about it. क्योंकि अगर ओमेगा ओमेगा I में से है, यानी अगर ओमेगा ओमेगा I में से है, तो x of omega क्या है? xi. So इसका मतलब ये है कि क्योंकि x ओमेगा I में से है, तो xi is equal to x of omega, तो xi की जगह पर I can substitute x of omega actually. So you're gonna have this sum. ठीक. And now एक दफा पहले भी मैंने बताया था कि if you consider each one of this, so x equal to x1 क्या होगा? is going to be a set omega 1, x equal to x2 is going to be another set omega 2, x equal to x3 is going to be another set omega 3 and so on and so forth. और अगर आप इन सारे omegas को यानी ये जितने भी omegas हैं, if you union them, say from I equal to 1 to infinity, so what you're going to get? You're going to get the entire sample space actually. So they partition actually the sample space. They partition the sample space. ठीक है? So if they partition the sample space, ठीक है? So I can write this as this is the sum for each omega in omega I. ठीक है? So this is what happening within omega I. And then if I want to see that okay, what is going to happen in entire omega I, then you need to sum them up for each of the I actually. So in other words, I can rewrite this sum as sum from omega in the entire omega. Okay, I hope you're able to see it. So this is going to be sum omega in the entire omega, okay, and times x of omega times what do you call the probability of omega actually. Okay. So this is like जो हर एक omega I में हो रहा था, if you put them together you're gonna get basically what is happening in the entire omega actually. Okay. So this is what is, so it's really much intuitive actually. And if you see, this is what you needed to prove actually. यही हमें चाहिए था. That the expectation that we usually write in this manner can also be written in this manner actually. So you have to keep two facts. To give the next key important result, I want you to keep these two facts in your library, in your head actually. एक ये that if you have to add two random variables and get a third random variable, then this addition is going to be pointwise. In other words, this is going to be on each of the element of the omega sample space. So that's a local sum actually. ठीक है? That you need to sum up over the each of the omega in the sample space. एक ये और दूसरा ये हमें करता है कि if you have expectation of x, ठीक है? The expectation of x can also be computed by taking each omega from sample space, compute what is the value of x at that omega, and multiply it with the probability of omega. ठीक है? तो ये दो facts ध्यान में रखने हैं, and then we can do. So let's do one example. इस तरह से computation करते हैं एक expectation. Let's try to do one expectation through, what do you call this definition? Why we are doing it? Because we are going to use these two facts to prove a very interesting theorem that कि अगर आप एक sum की expectation compute कर रहे हैं, so if you want to compute the expectation of sum of the random variable, then this is basically the sum of expectations actually. So this is what is going to be. So here's an example. Here's an example. This example is 9b in Ross. So suppose you have two independent random variables, two coin flips. So I have two coin flips. ठीक है? And x represents the number of heads. Now what is going to get into the sample space? Sample space क्या होगा? So you can have, the outcome could be that either both could be head, one could be head and a tail head, or both could be tail. And if you see what would be the x of, say, tail, so x of tail is basically 1. No, sorry, 0. Okay, so this event, okay, so this TT is like the event when x is 0 actually. Okay, and what would be the x of HT? So it's going to be 1, and what would be the x of TH? So it's also going to be 1. So मैं ये कह सकता हूँ कि भाई when I'm writing x equal to 1 in a set, what actually I'm saying is that, okay, there are two events, okay, two outcomes, HT and TH, they give you x equal to 1. So x equal to 1 corresponds to two outcomes. And what is the third value that it takes? Say x of HH, so it takes the value 2. Okay, so corresponding to this, you have the event, what we call head. Okay, this is what it's going to be the outcome corresponding. Corresponding, what was it? TT. And if you see, if you take the union of these, you get the entire sample space. Okay. Now, if I want to compute my expectation by this definition, so what I need to do? I need to take each of these outcomes and multiply it with the probability of it actually. So let's take, say, x of, say, TT and multiply it with the probability of TT. So the other is x of TH and multiply it with the probability of TH plus x of ht, multiply it with the probability of ht, and finally say x of what do you call hh, and multiply it with the probability of hh. Okay. So if the probability